In this session, I shall prove 5 properties of differentiation. First one, I have a function y equals to a constant a times another function. So both y and u are functions of x. And let me write this out. I can say that where I'll write it out this way: y equals to y bracket x, meaning that y is a function of x. U is equal to u bracket x, that's a function of x. And a is a constant, meaning that if x changes, a remains the same. So that's what this means. In this first property, if y is equal to a times u, then dy dx would be equal to a times du dx. And what this property is saying is that if it often happens that we know the answer when we differentiate a certain function, and then we need to know what to do if we have some number times that function. How would we differentiate that? Well, what this rule is telling us is that all I need is to differentiate this function first, if I know this, and then multiply by the constant. That's the first one I want to prove. The next one that I want to prove is if y is equal to a function u plus another function v, alright, where v is a function of x, another function of x. Suppose that I know how to find du dx and dv dx separately. Question is, what if I add u and v together to form a new function? Then how would I differentiate that new function? Well, this property tells us that all we need to do is to take the separate du dx and dv dx. That means we differentiate them separately and then we add them together. So that's the next thing that I want to prove. Number 3. Number 3 is the product rule. The product rule says that suppose y is a function u times another function v, and I want to find dy dx. I want to differentiate the function that is formed by multiplying u and v. So suppose that I know how to differentiate u and I know how to differentiate v. So is there a simple way to find the product, the result for differentiating the product? Or a simplistic guess might be to take inspiration from here and say that maybe I can differentiate them separately and then multiply them. Well, unfortunately, that does not work. In this case, the rule is that we can keep one of the factors unchanged and differentiate the other one first. So like say du dx times v. and then I would keep u unchanged and differentiate v dv dx, and then multiply that by u, and then add them together. So this is how to do it in this case, and this is called the product rule. Part 4 is the quotient rule. In this case, what if, suppose that we have a function y, which is the function u divided by another function v. Once again, if we know the separate du dx and dv dx, if we know how to differentiate these separately, can we use those results to find dy dx, to find the derivative of this quotient without doing a separate differentiation? The answer is we can, and this is the quotient rule. V would be v squared in the formula, and then on top I have v du dx, and then I must have u dv dx. So looks, the separate terms are the same as the terms in the product rule, except that in this case I have to subtract them. And this is the quotient rule. And the fifth and last rule, property that I want to prove, is the chain rule, which is very useful. The chain rule is for a composite function. Suppose that y itself, y is a function of, suppose that y is a function of another function of x. So y is a function of u, and u is in turn a function of x, a composite function. And suppose that we know how to differentiate y by u, and we know to differentiate u by x. Okay, so we can differentiate let's see. If I think of y as a function of u, that means that I would let's see, I would want to find dy dx, and I want to, and suppose that we know how to differentiate y with respect to its variable u, and suppose that we know how to differentiate u with respect to its variable x. The chain rule tells us how to then find dy dx for the composite function, and the answer is simply dy du times du dx. Okay, this is the last one that I want to prove. So let's start. Let's remind ourselves of the first rule. It's where a function is multiplied by a constant. We want to prove this. To prove this, we would start with, okay, let me copy this out again. If y is equal to a times u, where u is a function of x, then dy dx is equal to limit as delta x tends to 0 of delta y over delta x. That's the definition of dy dx. Delta y is the increase in this function when x increases by delta x. At first, this function is just a function of x, a times u, which is a function of x. If x increases by delta x, this becomes a times u bracket x plus delta x, right? And the increase delta y would be the difference. All right. To go to the next step, we notice that there is a common factor of a, which we can factor out. Now, in such proofs, we can often take some inspiration from what it is that we are trying to prove. We are trying to prove this expression, this relation between dy dx and a times du dx. Alright, so it helps if we also think about the definition of du dx. So let me write down the definition of du dx and see if it helps us to think of the next step. Okay, du dx is equal to the limit as delta x tends to 0 of u x plus delta x minus u of x. So that's the change in u divided by delta x. Alright, which the other way of, the shorter way of writing this is the delta u delta x. So delta u is the change in u when x increases by delta x. If we now look back at this, if you compare those two, you see that they have a lot in common. In fact, they are exactly the same except for the common factor of a. So clearly, if I factor out the a, what remains is just this, which in the limit should become that, which is exactly what we want to prove. So therefore, the remaining steps are quite obvious. If I carry on with the dy dx, I would factor out the a, okay. I would write out the remaining terms, u of x plus delta x minus u of x divided by delta x. And then I would say that that is the same as that. So in the limit, when delta x tends to 0, this becomes du dx. which is what we wanted to prove. So this completes the proof for the first property. Next, move on to this one, where we want to prove that if we have y equals to u plus v, then dy dx is the sum of the separate derivatives. Y equals to u plus v. Alright. We start from the definition again. This is the limit. Delta x tends to 0 of delta y by delta x. I'll draw a long line to prepare for what I need to write down. Now, delta y is the increase in those terms added together. So before, so at first, all right, before x increases by delta x, we have just u plus v as a function of x. But when x increases by delta x, u would increase by delta u, and v would increase by delta v. Okay, the sum is just like that, just adding them together. And this is what we would have after x has increased by delta x. So this is u plus v after x has increased by delta x. This is before. So therefore, the difference would be the change of u plus v. And that would be the change in y, which is delta y. Now we can simplify this. U and u cancels, v and v cancel. That leaves delta u plus delta v over delta x. Now I can separate those two, delta u, delta x plus delta v, delta x, and it just by the symbol itself, it is now clear that when delta x tends to 0, that tends to du dx, and that tends to dv dx, which is what I wanted to prove. That completes number 2. Moving on to number 3, the product rule, y equals to u v. This will be the limit as delta x tends to 0 of the change in y. So since we're getting more familiar with this, let me go straight into writing down an expression for the change in uv. Now at the bottom we have delta x. On the top, before x increases, uv is just uv. They are both functions of x itself. After x has increased by delta x, u would increase by delta u, v would increase by delta v. So uv now becomes this times this. Alright. And the change in uv from there to there is the difference. And with this we can expand and try to simplify the expression. This gives uv plus u times delta v plus v times delta u plus delta u times delta v minus uv. And uv and minus uv become 0, so those cancel. Let's write out let me separate those into 3 fractions. This would be u delta v over delta x. That would be v delta u over delta x. And that would be delta u delta v. I can think of this as both of them together over delta x. Now, but it's going to be more convenient. We'll see why in a moment. And that should be v. If I just choose one of them to be over the delta x, I can choose any one. Let me just choose that to be over delta x. Okay. So this was where we were. Now I can let delta x tend to 0. Then delta v over delta x would tend to dv dx. Delta u over delta x would tend to du dx plus delta v over delta x would tend to dv dx. Now delta u would tend to 0, right? Because delta u is the change in u when x increases by delta x. If delta x tends to 0, that means there's no increase in x, so there is no change in u. Therefore, delta u tends to 0. So therefore, this is 0 and we're left with this, which proves the product rule. So this is the product rule. And we've got that. Now moving on to number 4, the quotient rule. Let me try and prove that. Y is equal to u over v. dy over dx. Let's write out the definition as before. Limit as delta x tends to 0 of okay, this would be a little bit more complicated. At the bottom we have delta x as always. At the top we want to write down the change in this when x increases by delta x. So before x increases, it is just u over v, right? Both functions of x. After x increases by delta x, u increases by delta u, v increases by delta v. So the difference is then the change in u over v. So it looks a bit, actually it looks quite cumbersome. Let's see how we might simplify this. Right. We should combine those into a single fraction. Now we have delta x at the bottom. I'll multiply those two denominators. Okay. So the numerator here would become v times this. And this times u. Right. I shall expand that. That's vu plus v delta u minus uv plus u delta v over this v plus delta v, v delta x. And notice that those two cancels. And I'm left with this minus this. Now here is where, again, it helps if we take a look at what we're trying to prove. So look at this. This is what we're trying to prove. The quotient rule. If you remember, we are looking at this thing where we have a du dx and a dv dx, and we have a v squared at the bottom. Now let's look out for how we might get those two. Du dx could possibly come from those two, and dv dx from those two. So why don't I separate these into two fractions? Let's have a look out for what we might do with the v there as well. If you look at this, you see a v squared at the bottom. Okay, and the dx has apparently come up into the numerator. So that suggests what we can do with at this time. The v squared at the bottom would probably come from here, the v times this, somehow. Maybe because delta v would tend to 0. Now let's move delta x to the top and form the two fractions on top. to make it look more like what we want to prove. At the bottom, then, we are left with v plus delta v times v. And on the top, right, those two have cancelled. Delta x, shall put it under delta u, under the delta v. And now you can see that it looks more and more like the quotient rule. Finally, let's allow delta x to tend to 0. Now when delta x tends to 0, both delta u and delta v would tend to 0, because delta u and delta v are the changes in u and v because of a change in x of delta x. If delta x is 0, there's no change in the v, so delta v is just 0. At the bottom then we have that 0, and we have v times v, which is v squared. And then delta u over delta x becomes du dx. Delta v over delta x becomes dv dx. And this proves the quotient rule. Finally, part 5, I want to prove the chain rule. So I have y as a function of u, which is in turn a function of x. Okay, dy dx the definition of this is delta y over delta x. Alright, now this is a little bit more tricky than the previous step, but actually quite simple once we know what to do. Once again, let's go back to the thing we wanted to prove. If you look at those two, think about their definitions. All right, let's write down their definitions and see if it helps. The definition of dy, du, and du dx, right? So this is the limit, as in this case delta u tend to 0 of delta y over delta u. That is the limit as delta x tends to 0 of delta u over delta x. Okay, this gives right, yes. And what we wanted to prove, right, was that when we multiply those two, we get this. So let's think about multiplying those two. Why might we get this if we multiply those two? Right, because we have delta u in the denominator here and delta u in the numerator. So maybe, just maybe, they cancel and you're left with delta y over delta x. So that gives us a good idea how to do the next step. Well, I can't just multiply those two because the limits are in the way. If I just multiply this directly with this. Okay, but what I could do is I can do it from this expression where I have this whole thing inside the limit. Right, the limit tends to 0. okay, I can write this as a product of those two. So I'll separate into two fractions where I move delta x to the other factor, and I'll insert the delta u here and here. So now we can see that when we allow delta x to tend to 0, delta u would also tend to 0, because delta u is a function of x. So if the change in x tends to 0, the change in u tends to 0. And the change in u, delta u tends to 0, is exactly what I would need for this limit to get the dy du. So therefore, this in the limit when delta x tends to 0 becomes dy du times du dx. And so I have proven the chain rule. Let's stop here.